Okay, class, so today we're going to talk about financial stuff, which gives a lot of light to why we have exponential and logarithmic, or at least an application to these, which everyone will have the need for. So we're going to talk about savings, so lump sum. So that would be when you're given like a large chunk of money that you want to put into a bank. It often occurs like if you inherit money, or sometimes if you just take one large chunk of money, say out of Bank of America, and want to switch it over that whole bank account to Wells Fargo, you're just taking a whole lump sum money, versus a savings payment plan, which is the common way people save money, is by putting, $100 away out of each paycheck and do that for 10 years. And we're also going to talk about borrowing money, which is really applicable for people who need to go out and buy a new car, or say go to college, take out lots of loans, and then have to pay it back. So we're going to investigate those. So the first one we're going to talk about is savings. So this is when we're taking a large chunk of money. So our P is the principal amount that we're going to start with. And we have two formulas: interest paid n times a year and compounded continuously interest. And we'll talk about those two. Both of those apply when you have one lump sum money, P, that you're going to put away. Like you get $10,000 inherited, you're going to put it away. So both of these, A has to do with the accumulated balance, the money at the end. P is the amount we start with. R is going to be the interest rate in decimal. T for both of these is time. And then the difference is, for the first formula, interest paid n times a year. In the problem, you'll say that the interest compounds 12 times a year, or every month. So n would be 12, versus in the second one, in the problem, it would say continuously compounded, or compounds continuously in the problem, so you'd know to use that formula. Okay, so for example, if it said in the problem that the interest compounded weekly, then your n would be 52, because there's 52 weeks in a year. Okay, so let's do some examples of each of these. So this first one is your parents deposit $1,000 into your bank. So that's how much we're starting with. So my P is $1,000. When you were born, earning monthly compounded interest. So that tells us we're going to use this first formula where n is 12 because it compounds monthly and there's 12 months a year. Our interest rate is 7.5%. So our R is 0.075. And how much do you have? Okay, so we want to find how much we end up with. So we want to find A on your 18th birthday. So after 18 years, T equals 18. So we're just going to plug it in. A is P, which is 1,000, times 1 plus R, 0.075, divided by N, which is 12, to the N times T, 12 times 18, N times T. Okay, so what you need to do is you need to plug this into your calculator. So I want you to pause it, make sure you can plug it into your calculator and get the same answer I do. So get your calculator. We're going to do 0.075 divided by 12 plus 1. Order of operations tells us we have to do the exponent. So we're going to do an exponent with parentheses, 12 times 18, close the parentheses. Press enter and then do times 1,000. This bit has to be at the end. We do inside parentheses, exponents, and then multiply. Okay, so when you get that out, you'd have $3,841.25 on your 18th birthday. If you did not get exactly 25 cents, so if you rounded more than once, then you're not going to get what I get. So I need to make sure that you can use your calculator appropriately. So definitely ask me in class if you're having issues with your calculator. Okay. The second example says your parents deposit $1,000, so that's P again, when you're born, earning continuously compounded. So that tells us use the PERT formula, continuously compounded. R is still 0.075. How much money do we have? We want to find A on your 18th birthday. T is also 18. So we're really just comparing these two. Compounds n times a year, 12, versus continuously compounded. So A is P, which is 1,000, E to the 0.075 times 18. So again, we can put this directly into your calculator. So you should have it out. We can do 1,000 times E to the, and then the parentheses are open, 0.075 times 18, close parentheses, press enter, and you should get out that you'd have $3,857.43 on your 18th birthday. So it's a little bit more than it compounded monthly. So continuously compounding is kind of a hard concept to kind of grasp. What is it? So if it compounds monthly, it's 12 times a year. Weekly, 52 times a year. Daily, 365 times a year. You can imagine every second it would compound more. Every half second it would compound more. You keep chopping the time up to smaller and smaller increments, and you eventually get to what would be like continuously compounded. Just a lot of compounds. Okay, so here's the more realistic savings plan formula. So this is when you want to put away a certain amount of money each month or each paycheck or every year or something. This is how the normal population saves money. So for example, we have our PMT. That is our, that's one thing, PMT. That's the amount of money placed into your account every compounding period. And in the problem, it'll tell you how many compounds a year, which is N. Look at compounds monthly. And for simplicity, if we make 12 payments a year, our compounds are going to be 12 times a year. These two numbers are going to be the same. Sorry, the number of times we make a payment each year is going to be equivalent to N. R is still our interest rate. T is still time, A is still the end amount. So this is a big formula. This is a large chunk of order of operations. So you definitely need to make sure that you can get the same answers on the calculator. So for this first problem, we have our first job, and we want to put $150 away. So PMT, that's one thing. It stands for payment. PMT is 150. Every paycheck, which is every month. So we're doing things every month, and our interest is compounded monthly. So our N is going to be 12, and our interest rate R is 0.045, because we put in decimal. We want to know how much money will we have if we keep saving for 7 years. So T equals 7. Okay, so we have what we need. We want to find out how much money we want, so we want to find A. Okay, so PMT, we're going to plug everything in. A is PMT 150 times 1 plus R 0.045 over 12 to the parentheses 12 times 7 NT minus a big 1, and all of that divided by R over N 0.045 over 12. Okay, so we're going to put this all into the calculator. So the way you need to do it, follow along, 0.045 divided by 12 plus 1, press enter, raise it to the power with parentheses 12 times 7, close parentheses, press enter, subtract 1, and then divide it by, with parentheses, 0.045 divided by 12, press enter, then multiply it by 150. So when you do that, you should get out that you'd have $14,778.09 after 7 years of putting just $150 away each month. So not bad. That's a large chunk of money for a little bit of money, at least when you're working full-time. That should be doable. So order of operations, just to remind you, because I want to make sure you can get this number and that you're not rounding 5 times in one problem. Do inside the innermost parentheses first, raise it to the exponent with parentheses, then subtract 1. When you divide, we need to have these parentheses here, so we divide by everything, and then finally multiply by the number on the outside. So ask me in class if you're having trouble with the calculator, because this is an exercise in using your calculator properly. Okay, so remember this $14,000 number. So let's just say instead we just put the money into the mattress. You're afraid of banks or something. So what we did was we took $150 each month, and we're just going to use dimensional analysis to see how much we'd have. So we would do this for 12 months in 1 year, and we do this for 7 years. So using dimensional analysis, just 150 times 12 times 7, which would give us our units, is $12,600. And this is the amount that we saved. Okay, so that's how much money we put into the bank. But in part A, we said that we got $14,778.09. So what's the difference? Okay, so the amount we get in the bank is $14,778.09, and then the amount we put into the bank, okay, was $12,600. So the difference when we subtract is $2,178.09, and all of that is in interest. Okay, and that's the bank giving us that money because we put the money into the bank and the bank gave us that. Okay, so some people might question, well, why is the bank giving you this $2,000? Well, one reason is for the next type of problem. It's because when you take out a loan, this is where the bank earns their money. Okay, so you're going to borrow money. So when you borrow money, you're going to take out a loan. So P this time, since it's a loan, is the amount that we start with for the loan. So this is called the principal amount of the loan. And PMT, that's one thing, payment, that would be like our monthly payment. So we have R and N would be like your monthly payment, and we plug it into this formula. You by no means have to memorize these formulas. You just have to know when to use which one and understand what all the variables mean. Okay, so here we bought out a new car for $10,000. So that's our P. That's our principal loan amount with an interest rate of 6%. So our R is 0.06, compounded monthly, so N is 12. Since it's compounded monthly, for the purpose of the simplicity of the problems, we're going to make monthly payments, right? Monthly N is 12. If you take out 5-year loan, so that means T is 5 years. So we're going to plug everything in and find out our monthly payment. How much is it going to cost each month to have that car? Okay, so it's $10,000 times R 0.06 over 12 all over 1 minus 1 plus 0.06 over 12 to the minus NT 12 times 5. Okay, so that is a lot of stuff to put into your calculator. Do the innermost parentheses, raise it to the power, do 1 minus your answer, press enter, do 10,000 times your numerator, and divide it by your previous answer. And when you do that, you should get that your monthly car payment is going to be $193.33. So that's how cars become affordable, is you pay $193 each month and you get your $10,000 car. So if we take our monthly payment, and our monthly payment is $193.33, so we want to find out how much we really paid. Well, we pay this each month, and again, dimensional analysis, 12 months for 1 year, and we're doing this for 5 years. So cross off, we can see that it's $11,599.80. This is how much the car really cost. Okay, so what's the difference? We paid back $11,599.80, but we only borrowed $10,000 for the car. So the bank gets the difference, which is $1,599.80 of interest. So when you save money, the bank can give you some interest because they're getting interest from other people for the loans. Okay, so there you have it. $10,000 car really cost you $1,600, or sorry, $11,600 because the bank gets a chunk of it. Now imagine how much a house is actually going to cost in interest, because houses are typically paid back over 30 years. So that's a long time for the bank to be earning interest. So there you have it. Some great applications for some exponential logarithm problems. And definitely check in with me if you're having calculator issues. So bring your calculators to class, and you have a wonderful evening.